Okay, welcome to Module 1, the overview of the course, Statistics for IT Managers, 95796 in Mini 5, the first half of the summer of 2023. I am this guy, John Ostlund, and I'll be your professor. This introduction is partly an overlap with the syllabus. So I hope you have also looked through the syllabus and seen the video for that. I will clip along and not repeat redundant stuff that much. Let's take a look at an overview for the course, how the course is structured, and Q&A. Of course, in my video recording, there's not going to be much in the way of Q&A from you folks, but in class there may be. So, what are the goals of the course? Well, this is going to be an accelerated introduction to probability, basic statistical methods, and regression for being able to do not only the kinds of statistical analysis that these basic things allow, but also to give you the necessary background so that you can take, whoops, a little too much yellow there, so that you'll be prepared for more advanced analytical courses later. We want you to be able to actually start using probability and statistics to answer real questions of your own or real questions from your boss or from your clients or from whoever else might ask you a question. We're also, along the way here, going to take a look at the idea of inference. For example, you might do a statistical analysis of a sample of data, and you might conclude that the mean price of homes in a certain state is X dollars. And that is a statistical fact that your sample gave you back this mean of X dollars. But we would like to be able to go further than that, and we would like to be able to ask questions like, has the price of homes in this particular state statistically significantly risen over the course of the last 5 years? How could we answer a question like that? Have the prices changed significantly? Have they risen significantly? And when we say significantly, what do we mean? How confident are we of the answer that we're getting to those kinds of questions? Okay, so here's a couple of example questions that we might use statistical analysis to address. When the internet came into use, one of the first commercial uses for the internet was online bookstores and stores for various other kinds of things. Amazon, most obviously. For quite a long time early, Amazon was only an online bookstore and then branched out into all kinds of other things. And you could ask the question, are prices of books lower on the web than they are from bricks and mortar shops? Well, you can gather all kinds of price data from various websites and from various bricks and mortar shops and do some kind of statistical analysis to try to determine whether book prices online are in fact lower. Or, as another example, if you provide people with calorie information about the food that they're eating in a store, maybe in a frozen dinner in a store or something like that, or in a meal that they buy in a fast food shop, does providing people with calorie information reduce, or for that matter, increase the amount of calories that they consume? Does the calorie information seem to have any impact on how people actually behave? Well, the first thing you could do would be to rely on intuition, and you could say, well, I've looked around, and obviously book prices on the web are cheaper than brick and mortar stores, and I've thought about it, and obviously if I give calorie information to people, they're going to reduce their calorie consumption. Well, that's all very nice, but you have no proof of anything. And like if you are working for an organization that's concerned about people's health, and you have been asked this question, look, if we give people calorie information, will that reduce the amount of calories they consume? Your client who has asked you this question is going to want some convincing evidence, not just your opinion. So as opposed to just relying on tuition, it's much better to gather data from the real world and then do convincing statistical tests to determine whether your intuition is correct or incorrect. You may very well have an intuition about what you think should happen, but your analysis could demonstrate that you're completely wrong. Okay, so in a nutshell, the purpose of statistics is to take raw data, which is usually this giant mass of unstructured stuff, and turn that into useful information from which you can make an actual business decision or healthcare decision or something like that. Okay. It's rare that people can simply look at raw data, like look at a list of prices of 1,000 books and draw accurate conclusions about trends of prices of books or whether online books are cheaper than books in bricks and mortar stores, et cetera, et cetera. So given this massive data about book prices, we want to do things like computing average book prices and differences between the averages for the web versus bricks and mortar store, and then apply statistical inference tests with what are called confidence intervals, for example, to determine whether we really believe that the prices of books online are statistically significantly lower than the prices in a store. Okay? The kinds of statistics that we might get can be in the form of just ordinary descriptive statistics. That is, we can simply state that, okay, we've gathered a bunch of data about prices for books in bricks and mortar store and books on the internet. And for our data, the average price on the internet is 20 cents lower than the average price in bricks and mortar store. All right, that's fine. That describes that given the data that you've collected, that your average is 20 cents lower. But if you think about it, even for just a few moments, it raises all kinds of questions about the amount and validity of the data that you've collected. For example, have you collected 10,000 records from the internet and 20 records from brick and mortar stores? In that case, you might have some serious questions about whether there's any meaning, any validity to this difference in the average of the prices. So we would like to go beyond. Descriptive statistics is good. Descriptive statistics describes what you found. But we would like to be able to go on to statistical inference and say, okay, we have done careful trials and gathered significant amounts of data from these different sources. And based on the amount of data that we have collected and our confidence that that there's not bias in the data that we've collected, that we have a 95% level of confidence that the average price of books on the internet is definitely lower than the price of books in bricks and mortar stores. Okay, so that's going to require a little more sophisticated statistics and mathematics than just the plain descriptive statistics part. Okay, so statistics is the business of analyzing and interpreting data. Okay, that is another way of saying the same thing, is that we are transforming a pile of unstructured raw data into usable information that we can examine and make decisions with. Descriptive statistics are just organized and summarized information. Whoops, pardon me. Too many clicks. All right, just organized and summarized information, typically in the form of graphs or numerical tables. Graphical displays of statistical and descriptive statistics are of many, many kinds. We have bar charts, pie charts, line charts, etc., etc. We're going to take a look specifically at histograms, which basically just summarize the data that you have collected into bucket ranges and show you how much data you have in these various ranges. And we're going to take a look at box plots, which is actually a much more sophisticated mechanism for summarizing both information about averages and information about spread and information about outliers within the data that you've collected. Numerical summaries are often presented just as values or as tables of values, things like the mean value or the average value, the median value, the spread or what's called the variance, or the standard deviation of the data, etc. Descriptive statistics are merely descriptive. You can look at descriptive statistics and you can make decisions about what you would like to do based on these descriptions, but it's not a very powerful mechanism. We would like to be able to move on to a more sophisticated level of analysis to see if we can actually make inferences about facts, about changes in things at certain levels of confidence. And in this case, what we're always trying to do is we're trying to find out something about an entire population of entities based on a sample drawn from that population. What am I talking about, population? Well, we can think of the population of people. We could think of the population of people on the planet. We could think of the population of people in the US, people in China, people in India, people in the European Union. And if we want to find out things like what is the average height of people in these places, what is the average household wealth of these people, what is the average age, these are all examples of things that we can learn, hopefully by selecting good samples rather than having to evaluate this information for every single person in this entire population. Okay, so let's suppose that in China there are about 480 million households, and we would like to know what the average income is for these households, among these 480 million Chinese households. Well, it's going to take lots of money and it's going to take lots of time to go around and analyze the average, the individual incomes of all 480 million of these Chinese households. It's just not really realistic to contemplate doing that. If we did that and we computed the average of every single income value for every single Chinese household, we would be able to compute what's called a population parameter, and the symbol that's used for the mean in statistics is this Greek letter mu. All right, mu, m, mean. All right, so mu represents the population mean of whatever it is you're trying to analyze. Well, so we don't want to go out and analyze 480 million separate households. Instead, what we would prefer to do is to draw a sample in some appropriate randomized fashion of, let's say, 1,000 Chinese households. And then from that sample, we can compute a sample mean. This is usually described as X bar in statistics. Okay, so we think of each income value of each household that we analyze as some value of X. X sub 1 would be the income of the first household, X sub 2 of the second household, blah, blah, blah. X sub 1,000 would be the 1,000th household. And we would get the average income of those 1,000 sampled households by just adding them all up and dividing by 1,000. Okay? And we describe X bar here, the mean of those X bar sample values, as an estimate of this population parameter. Okay? So that's what inferential statistics is about. We are trying to learn things about an entire population, but analyzing the entire population is too time-consuming, too expensive. So instead, we carefully select a representative sample and draw conclusions based on that sample. All right, so that's just a little conceptual taste of what it is we're trying to do. Let's take a look at the organization of the course. Some of this, as I said, is going to be redundant with what we talked about in the syllabus. This is me. Junyu is our TA. I will have office hours by Zoom every Saturday from 3:30 to 5:30 p.m., and I will post the link for that Zoom session. In terms of the structure of the course, basically the course is divided into 4 separate modules. The first of which is going to be graphical and numerical representations of summary statistics. Okay? Then we're going to take a look at how to compute probabilities, how to compute probabilities of combinations, and how to compute what are called conditional probabilities. This will give us the algebra that we need in order to be able to compute probabilities of certain events based on what we already know about probabilities of other related events. After we have handled descriptive statistics and we know how to manipulate probability analysis, we'll be all set up to do statistical inference, where we can state that we are, 95% confident that the mean of the population is greater than some other specific value that we've selected. And after we've taken a look at statistical inference, we're going to look at regression. Now, each week, there are going to be some so-called worksheet problems for you to do between the Monday lecture and midnight Thursday. On Friday, during the problem-solving session in the morning, I will go through the problems described in that worksheet, and we will solve the problems and talk about approaches to solving the problems and so forth. Now, the deal about these worksheet problems is that you are going to be graded on whether you make a legitimate try at solving them and whether you successfully hand in your finished worksheet on time. There will actually be no grading based on whether your answers are correct or not. So we want you to do your best at solving these worksheet problems so that we will all be set up and ready and knowledgeable about the problems for the review on Friday. But other than the fact that you have to take them seriously and hand them in, there is not any grading associated with these submissions. Now, I'm going to recommend that you use ISLE, which was developed by Dr. Philip Burkhart in the CMU Statistics Department to do your statistical analysis. ISLE is an extremely simple statistical analysis tool. You should have received an invitation to join ISLE by email in the last, probably during the weekend sometime. To gain access to ISLE, start your browser, and we recommend Chrome or Firefox on Windows. Safari, yes. Safari on a Mac should work fine. Forgot the name there for a second. Internet Explorer apparently has some kinds of problems with ISLE, so avoid using Internet Explorer on a Windows box. You can browse to isle.hines.cmu.edu, and you should get to ISLE, and you should see among your courses this 95796 course. That's probably the only course that you'll see among your courses. And if you click on that choice, you will see various data sets that have been created for this course and also various computational widgets that have been included for us to use in this course. And we'll be talking about these various data sets and widgets as we go. All right. Now, if you run into technical issues, you can't access ISLE, it's just not coming up for you on your machine, things of that nature, you can directly contact Professor Burkhart and ask him such questions. But any other questions about course-specific things, like what we're talking about in this course, homework assignments and worksheets assignments in this course, and actually the various contents of these specific data sets, like this fast food experiment, which I'll be using in my discussions in the next few lessons. He is not going to be able to provide you, and frankly is not going to want to spend time providing you with information about those things. So direct those kinds of questions to me and our TA, and only technical problems with ISLE itself to Professor Burkhart. All right. Okay, so as I said, you're expected to try the worksheet problems so that we can talk about them on Friday. You have to submit your attempts before midnight on Thursday prior to the Friday review session. You may wish to work as part of a group. You can create a group of your own of up to 4 people. If you would like to work as part of a group, but you don't know other people in the class, send me an email about that, and I will create groups of people to work together on these worksheet problems. Okay, now each person needs to submit their solution. But we realize that if you're working as part of a group, all of the members of the group are going to have identical solutions, or at least very close to identical solutions. And that's fine. We simply ask that you, when you submit your solution, provide all of the Andrew IDs of all of the people in the group, so that we know if your solution looks identical to somebody else and that person is in your group. That's the explanation as to why. Okay? Now, on Friday, I will ask for each question whether someone would like to present their own solution to the question. You are welcome to volunteer if you would like. However, I want to just make clear that we're not going to give extra credit for doing this. This is just something that you are welcome to do. If you're interested in the problem and you feel like you got a good solution to it, and you'd like to demonstrate that, we're happy to let you do that. In terms of grading, the worksheet problems will be 20%. The homework assignments will be another 20%. The midterm quiz will be 25%, and the final exam will be 35% to bring it all up to 100%. Here are when things are due. This is also repeated in the syllabus. We are using a textbook. The particular, okay, so historically this course has used a book called Statistics for Business and Economics by McClave and Benson and so forth. We never assigned the most current version of the book because this information that we're studying about descriptive statistics, probability, inferential statistics, and regression, none of this material has changed in any appreciable way in decades, and all of these books cover it fine. So the 13th edition is 1 or 2 editions old, and you ought to be able to find that for $30, $20, $10 used or as a PDF somewhere. And if you can't, then you can look for the 12th edition or the 11th edition or whatever, okay? And I will mention, it is mentioned in the syllabus, which sections in the book correspond to the particular material that we're talking about. Okay, the final thing I want to mention is, just like my discussion of the syllabus, and just like my presentation of Module 1 here, I do plan to pre-record all of the material and post these videos on YouTube. So if you would like to review things after you've watched the lecture, or if for some reason you're not able to make it to a lecture because of a work conflict or travel or whatever it might be, you can always catch things on video. Also, although I mentioned this in the syllabus, I forgot to mention it here. We are either lucky or unlucky in that 2 of our 6 possible lecture days are federal holidays when CMU is actually closed. So, on Monday, May 29th, that's Memorial Day, and we will not have a live lecture. Likewise, on Monday, June 19th, that is the Juneteenth holiday, and we will not have a live lecture on that day either. So on those two particular days, the 29th or the 19th, either before the day or after the day, but near the day, please do watch the pre-recorded video that I will have posted. Okay, now I just wanted to point out a couple of things in this aisle interface here. One of the examples we're going to take a look at is this fast food experiment, which has to do with whether giving people calorie information modifies how many calories they consume. So if I go to this fast food experiment dataset and click Open Lesson, it gets pulled in. And here on the left side is the table of data. Now, there are a variety of attributes for each observation here. What is the subject's ID number? That's just an arbitrary number assigned to each subject, and that's just, you know, the IDs are 1, 2, 3, 4, 5, etc. Did we provide this particular subject with calorie info or not? 1 means that the person was provided with calorie info. 0 means they were not. We ask each participant to rate their hunger level from 1 for not hungry to 7 for very hungry. We ask them whether they're dieting currently. We ask them whether they're vegetarian. We ask them their age. We ask them their weight, their height, blah, blah, blah. Okay? Bunch of stuff in here. And what we're interested in knowing is okay, here is the total calorie column. And by the way, when you click on a title, that will sort the column in ascending order. So the total cal column shows the total amount of calories that the subject consumed during their lunch, and these are based on the calories registered for the different items that are available. So that's why these numbers, we have 345, 390. We don't have 356 and numbers like that. We have the numbers that are actually provided as the calorie information by the store that's selling this stuff. And we're interested in knowing if we gave people calorie information, did they consume fewer calories, statistically significantly fewer calories, than if we did not give them calorie information? All right. Now, over here on the right side is where we're going to see a variety of outputs shown. So let me fire up the toolbox of things we can ask for. Let's just ask for some plots. And here is a histogram of, let's ask for a histogram of the weights well, I'm just going to ask for the weights of everybody. And I'm going to ask for automatic binning. So we'll generate this plot. And there we go. So here is our histogram showing the weights of the participants in our study binned into 10-pound wide bins. So we've got from 90 to 100 pounds, and from 100 to, well, from 90 to 99 pounds, from 100 to 109 pounds, from 110 to 119, and so on. And we see that there is a sort of a mound-shaped mound shape to this histogram. In our sample, the the most common weight was in this 160 to 169 area. We did have some people that were, 250 pounds and above, although not very many. All right, so that's just one trivial example of using aisle to do some analysis of this table. All right, onward ho.